Now let us see a theorem. Let xn be a sequence of real numbers and let x belong to R. If an is a sequence of positive real numbers with the limit of an equal to 0, and if for some constant c greater than 0 and for some m belong to n, modulus of xn minus x is less than or equal to can for all n greater than or equal to m, then limit n tending to infinity xn equal to x. Listen, if xn is a sequence of real numbers, x belong to R, an is a sequence of positive real numbers with whose limit is equal to 0. Then for any constant c greater than 0 and some m belong to n, if modulus of xn minus x is less than or equal to can for all n greater than or equal to m, then this xn converges to x. So let us see what are given. An is a positive sequence of positive real numbers whose limit is equal to 0. So we have start with an epsilon greater than 0. Given that c greater than 0, then we have epsilon by c is also greater than 0. Since limit of an equal to 0, we can choose a k belong to n such that modulus of an minus 0, an converges to 0, so modulus of an minus 0, which is equal to mod an. But mod an equal to an because an is a sequence of positive real numbers, so an less than epsilon by c for all n greater than or equal to k. Then if we choose n greater than or equal to k and n greater than or equal to m, or we may write n greater than or equal to maximum of k and m, then modulus of xn minus x less than or equal to can. An is less than epsilon by c, so can is less than epsilon for all n greater than or equal to k and m, or greater than or equal to maximum of k and n. Therefore, limit n tending to infinity xn equal to x. And next we give some applications of this theorem. So once again let us see the statement of the theorem. If xn is any sequence of real numbers and x is a real number, an is a positive sequence of positive real numbers whose limit is equal to 0, and if mod xn minus x less than or equal to can for all n greater than or equal to m, then actually mod xn minus x also tend to 0. In other words, limit of xn equal to x. So let us see an example. Suppose a greater than 0, then we prove that limit n tending to infinity 1 by 1 plus na equal to 0. Note that 1 by 1 plus na is less than 1 by na because the denominator is less here, and which is equal to 1 by a into 1 by na. So given that a is positive, so 1 by a is positive, and we know that 1 by n tends to 0 as n tends to infinity. Then by that theorem, put c is equal to 1 by a, we have modulus of 1 by 1 plus na minus 0, which is nothing but 1 by 1 plus na less than or equal to 1 by a into 1 by n, and this tends to 0. Therefore, limit n tending to infinity 1 by 1 plus na equal to 0. Now next is very important. This if c greater than 0, then limit n tending to infinity c raised to 1 by n equal to 1. For any positive c, limit n tending to infinity c raised to 1 by n equal to 1. So we split the proof into 3 cases. If c equal to 1, if c equal to 1, c raised to 1 by n equal to 1 for every n, so that is nothing but the constant sequence 1, 1, 1, which is definitely convergent and which converges to 1. Next we take c greater than 1. If c is greater than 1, for every n, c raised to 1 by n is also greater than 1. So, if c raised to 1 by n is greater than 1, we can write c raised to 1 by n equal to 1 plus dn for some dn greater than 0. For all n, we may write c raised to 1 by n equal to 1 plus dn. Actually, we take dn to be equal to c raised to 1 by n minus 1. Okay, then we have c raised to 1 by n equal to this, so that c equal to c raised to 1 by n the whole raised to n. That's equal to 1 plus dn the whole raised to n, which is greater than or equal to 1 plus n dn by Bernoulli's inequality. Hence, c minus, you consider these two parts, c minus 1 is greater than n into dn. So, dn is less than c minus 1 by n. So, modulus of c raised to 1 by n minus 1, that is dn, less than or equal to c minus 1 into 1 by n. Since c greater than 1, we have c minus 1 greater than 0. So, again by that theorem, and also because 1 by n tends to 0 as n tends to infinity, again by theorem 3.1.10, limit n tending to infinity, c raised to 1 by n equal to 1. So, for c greater than 1, we have done this. Now, suppose c less than 1, then c raised to 1 by n less than 1. If c raised to 1 by n is less than 1, its reciprocal is greater than 1. That is 1 by c raised to 1 by n is greater than 1. Put hn equal to 1 by c raised to 1 by n minus 1. So, we have, by rearranging, we have c raised to 1 by n equal to 1 by 1 plus hn, and clearly hn is positive. Therefore, c equal to c raised to 1 by n equal to 1 by 1 plus hn. So, c is equal to that whole raised to n, that is 1 by 1 plus hn the whole raised to n, which is less than or equal to, here in the Bernoulli's inequality we take the reciprocal, so this is less than or equal to 1 by 1 plus nhn, which is less than 1 by nhn. So, from this we have, so c is less than 1 by nhn, so hn is less than, this n is the suffix for h, hn less than 1 by nc for n greater than or equal to n. So, we have 0 less than 1 minus c raised to 1 by n equal to hn by 1 plus hn, which is less than hn, which is less than nc. So, we have 1 by c raised to 1 by n minus 1 less than 1 by c into 1 by n. This c positive, so 1 by c is positive, 1 by n tend to 0, then by that theorem we have limit n tending to infinity, c raised to 1 by n equal to